Hello, my name is Tarık and I'm a PhD student at Northeastern University. In this talk, I will present our work on learning based filter models for tactile localization. Many manipulation tasks benefit from tactile perception, such as grasping, in-hand manipulation, and tactile localization. In literature, tactile localization is formulated as the problem of inferring the object pose or inferring the gripper pose. Although the object pose estimation problem is explored by many researchers, the work around the estimation of gripper pose has been limited. Furthermore, the current localization methods for grippers are not generalizable to unseen environments. In this work, our aim is to build a method for estimating pose of robotic grippers while they are interacting with the world. Formally, we would like to localize a gripper with respect to an image of the environment using tactile feedback. We formulate our problem as a base filter which maintains a belief of the state. Base filters update the belief by using an observation and a motion model. In our work, these models are unknown, so we propose to learn them from data using neural networks. In the problem formulation, the state space is defined as the pixel coordinates of the gripper in the environment image, and the observations are history of finger joint angles. To learn the observation and motion models, a neural network architecture is proposed. The architecture has four modules. The image encoder takes the image of the environment and passes it through 2D convolutional layers to produce feature maps. Similarly, the observation encoder takes the tactile feedback and feeds it into 1D convolutional layers. The output of these two encoders are combined and passed through a 2D convolution decoder, which generates the likelihood map. These three modules form our observation model. For the motion model, we use single 2D convolution layer that takes the previous belief and transitions the state to the next belief. The predicted belief and the likelihood map are then multiplied element-wise and normalized to generate the next belief. To train and evaluate our model, we developed a simulation environment using Mujoko physics engine. The simulation consists of a table, objects, and a gripper. During data collection, the gripper is swiped over objects. At each episode, we sample different object shapes and randomly place them on the table. A top-down depth camera is placed over the table. We collect images of the environment, pixel coordinates of the gripper, and the tactile observations for every time step. After training the base filter models, we evaluate our method on two scenarios. In the first experiment, we use primitive shaped objects which are also used in the training set. An unseen environment is generated by sampling shapes and sizes of these objects to show the generalization over different configuration of the objects. In the second experiment, we use objects from the YCB object set. The second experiment aims to show that our method can generalize to new objects. For each experiment, we run 64 episodes and record the localization error at the end of the episode. The Manhattan distance is used as the error metric. The mean localization errors of the episodes are found to be 1.15 for primitive objects and 5.7 for the YCB objects. We also show a video of belief updates as the gripper moves and interacts with the environment. In summary, we proposed and evaluated a visually conditioned tactile localization method for estimating the position of grippers using tactile feedback. We showed that observation and models of the base filters can be learned from data. We also showed that our method can generalize to unseen environments and objects. For future work, we would like to extend our method to learn policies for contact-rich tasks using belief as the input to the reinforcement learning. Thank you for listening.